limited by physical limitation. We always limited by physical limitation.
You can have arbitrary randomness.
See, compressed sensing is really what I said on my slide. It's an interpolation problem. Where was my slide? Compressed sensing is I can sample in the spectrum where I want, and so I have to interpolate. It's a bit like what we do when we do linear regression. Here I sample only in the middle, I have to extrapolate. And that's dangerous. And that's why sparsity alone will not allow you to extrapolate.
Yeah, another question.
You just mentioned briefly in one of the slides that we can obtain 3D, the depth information from 2D image, and you mentioned something about the point square function. I didn't catch up the idea behind that.
I'm glad. I'm glad you asked all these great questions because this is really a very neat paper by this guy. So I'm going to write his name. The idea. Do you know about optics?
Excuse me?
Do you know about optics?
By optics?
Optics.
Optics. Yeah, maybe a little bit.
The idea is, there is a clever idea here, which is that, well, you see, you have an imaging cube now. So you have your cube like this, okay? Now, molecules are in X, Y, Z, they are here. And so they're going to fluoresce. Now the fluorescent light is going to be collected on a phase plate. So if you had simple optics, this would be an aperture, so you have a lens, an aperture, an other lens, and then you collect the light, right? Except that what Werner does, so you have a lens, and you have an aperture, and you have another lens, and then you've got your image. That's a 4F system. Now, suppose that now in Fourier plane I do something. I actually put the phase mask. So I mess up with the phase of the incoming light in such a way that if the light comes from deep, I'm going to do a different thing to it than if it comes from close. Okay? Now, what that means in this double helix scenario is that when I look at an image of a point source over here, after I use my phase mask over here, I'm going to see different things in image plane. And so, I can show you the papers where this is explained, but basically the idea is to put a phase mask in Fourier planes right here. And so what that means is that if you are here, like maybe the PSF of a point source at this depth would look like this. It's going to have two lobes like this. A PSF at this depth, on the other hand, would look like this. A PSF at this depth, intermediate depth, would look like this. So by looking at the angle of these lobes, I kind of know I know depth. Okay, and that's achieved by putting a code in Fourier plane when the wave passes now. And so this is neat because it says that now all of these things project, and by looking at the orientation of the PSF, you have an idea about depth. So you can recover some 3D structure from 3D data.
Is this a work, long existing work or very recently work?
The double helix paper, they were published, I think 2010, in the Proceedings of the National Academy of Science, I believe. 2009, 2010, kind of recent.
Maybe I can check the paper for more details.
Anyone else questions? Okay.
that's a good question again, and that's a question I have to deal. Whenever I work with engineers, we design systems, that's always what they ask. How do I know the thickness point? I don't know. Sparsity is a trend, right? It's not a number, it's a trend. So in compressive, now I think we can leave the light on. And that's why I spent a bit of time explaining this. What I can give you with compressed sensing is that I can take 1,000 measurements. Let's be very concrete now. That's what I tell engineers I work with all the time. I said, I can take 1,000 measurements. That's what we're going to take. I said, which accuracy are we going to get? This I can't tell you, but here's what I can tell you. So from these 1,000 measurements, I will get the accuracy which is the same as if I could see the whole signal and keep the 250 largest entries. So I can achieve the same distortion. That's all I can say. Is this a small distortion? Is it a high distortion? That depends on the signal. Is the signal well approximated by its 250 largest entries? Well, that depends on the signal. If the signal is simple, yes it is. If it's white noise, no it is not. And so, as I mentioned on Monday, to me an important thing that is a bit missing in the whole theory of compressive sensing, I feel, is, so let's be very practical here. And that's stuff we work on this and we have answers to this based on cross validation and resampling techniques and so on. But the thing is, you imagine this ball comes in, you press a quick scan button, instead of taking 2 minutes, it takes 10 seconds to get an image. And the doctor says, how accurate is it? What are you going to say? If I take another 10-second scan, how much could you improve? And so to be able to kind of assess just by looking at how far you are from the truth is very important. And I think this is a subject that needs a lot of research. We have some clues, we know what to do in some cases, but not always. Okay?
I'm an engineer as well. Just curious, where you were working on these problems, how do you get these kind of tools?
How what?
Because a lot of this is about imposing conditions such that the problem becomes solvable, right? How do you get tools?
How do I get one?
Clues. Some ideas. How the idea. How to solve it.
See how you eat. How do I get clues? Me?
Yeah. A lot of people, a lot of young people, they want to give certain advice.
So you ask, why is it that I do the things I do and stuff like this, right? Okay. I spend a lot of time listening to what other people do completely outside of my field. So for example, I would not have started the field of compressed sensing if I had, when radiologists called me, I had said, no, I'm not interested in talking to radiologists. So these radiologists called me and I picked up the phone and I listened to what they said. And I thought that, the reason they called me, that they thought that I had some knowledge that could help remove artifacts. So they were showing me, they say, Emmanuel, we want to speed it up, we subsample, but it's not working, we're really worried because we see this. And can you help us get better than this? And then you think about it and so you say, yeah, that's an interesting problem, maybe I can do a bit better. And then you say, well, you get this. Okay? And that's the kind of, and then you're very surprised because why is it exact? Like you expect to get something that looks better than this, but not this. So it's exact. And then I think it's a big difference. I say, so for me, like, first of all, you listen to people. You don't stay in your field. You go, you listen to what people have to say. You try to get inspiration for your research from what happens in neighboring fields. I think for me it's extremely important. I go to lots of conferences that are not in my field. I go to lots of seminars at Stanford that are not in statistics. Two, sometimes you stumble across something that is surprising. You run an algorithm and it returns the truth. Now you have two types of people. People who just say fine, return the truth, and then they don't ask anything more. And people say, why is that? I'm the type that would say, why is that? Does it generalize? Can I do other things? And so this is a bit how am I working. So I'm really like, I get a lot of inspiration from what I do from other fields of research. And I try to port other fields of research into my thing, because I think that's what math does. You have very concrete problems and you try to find the right abstraction for them. And you find the right abstraction for them. And then what's beautiful about mathematics and quantitative thinking is that you find the right abstraction, and not only you kind of solve an MR problem, but you solve 100 problems like it. And so by discovering this, and you discover that you can compress and acquire simultaneously. So I think the message is listen to what other people say. That's been very useful for me.
Particularly your wife.
Yeah, my wife. Exactly my wife.
Before ending the talk, we have.
Can I say one more thing? If you want? On Tuesday or Monday, I talked about another thing that is quite hot at the moment, which is matrix completion. That I heard on the radio. I was on the radio. I was driving to Caltech. I remember there was this radio program where they talked about the Netflix challenge. And I thought, that is very interesting. And then I arrived at Caltech, I stopped what I was doing, and I thought about the Netflix prize. So it may not be your colleague at Stanford, it can be, NPR or PBS. It can be National Public Radio. It doesn't have to be, it can be sitting next door.